Introduce Jan Mináč from Western University. We're very happy that he'll be speaking for us today. He'll be speaking about the charm and mystery of absolute Galois.
So thank you very much, both Spyman and Kumai, and also Zahir to arranging all of these things. I very much appreciate it. This is a wonderful opportunity for me to speak in the seminar. I want to begin with apology a little bit. I am not accustomed for Zoom delivering lectures, so if I do some funny things, please bear with me. So I will begin with the kind of my feeling about Galois group themselves. There is something extremely deep, elegant, and relevant in Galois groups, and it is all the time. It is for mathematics, for physics, for chemistry, and so. And it is. I learned about Galois theory when I was teenager, but the excitement and refreshment and is kind of still with me. I still feel fever whenever I'm thinking about Galois theory. So it is a great pleasure to now let me go to the second slide. So you can see this is not so well known that the mystery of absolute Galois group was also investigated by Sherlock Holmes and and Dr. Watson and his team. So that is here little slides. And now here are some of my friends, students, and colleagues. I will read from the screen. You can read yourself, but let me still perhaps read it. Who contributed to this work on this absolute Galois group. So I cannot introduce all of these colleagues, but I will point at some of them who will play the role in my talk. Like, for example, here is Ido Efrat, here is Sasha Merkuriev, Federico Scavia, there is Andrew Schultz, Zinovia Einstein. So many people. All of them has some input. Adam Topas and Christian Meyer. So, Tung is here, so it's a great pleasure to introduce this. This picture was taken last June on the workshop of massive product. Okay, so now the plan of the lecture is to tell a little bit about absolute Galois groups, then concentrate on the small important quotient of absolute Galois group, mention Earth-Voevodsky theorem, but I will not dwell on this too much. I will just mention some consequences of Earth-Voevodsky theorem, and then on massive vanishing conjecture. So let me recall from abstract that key thing which I want to concentrate on this lecture is the following question. From the very definition, we shall come over it, but let me tell it also before it, that absolute Galois groups are for per finite group by the very definition of them. And now the question is, how do you classify absolute Galois group of fields among other per finite groups? And it is a very mysterious question. We know some spectacular theorem like Earth-Voevodsky theorem, which tells how specials are the absolute Galois group. And however, and there are some other theorems which I will mention. However, we seems to be quite far from complete classification of absolute Galois group of fields among per finite groups. One of the recent things which I like very much is massive vanishing conjecture. This is a conjecture which we made with Stan. And this could put another light of absolute Galois groups. So let me now. So here is again, thank you to Kumai and Paiman, and this is supposed to be me leaning to thank them. And so now I can begin the lecture in proper. So here is a basic notation. I hope that everybody can see. Paiman, you can see the full screen, right? So okay. So yeah, I begin. So I assume that F is a field, P is a prime number, F cross is a multiplicative group of fields. So it is of course a field that they take away zero. And zeta p is a primitive p-sort of unity. And this means the line below is that the subgroup which is generated by ZP of F cross is ovoid IP. So in other words, you simply exclude the one. Yeah, it has to be, yeah. So, and then F separable is the separable closure of F. Now, finally, we come to the basic definition of absolute Galois group of F. So this is just a call for most of you are very familiar with this. So absolute Galois group is the Galois group of separable closure of F over F. But this can be viewed also as a projective limit of finite Galois groups, where K over F is finite, and K over F, of course, is Galois. Otherwise, you could not take Galois group of this. And so by when you believe that this is equivalent to this, then this Galois absolute Galois group is clearly per finite group because it is projective limit of finite groups. Okay, so that's what I mean by per finite group. So in particularly, it is a topological group. And now, similarly, you can define FP extension, similarly to separable closure, FP extension, which sits inside of separable closure. And let me put the slides below. So this is union again of all finite separable extension, but now the degree, there's a further condition is of this, they are Galois, but the degree is also P2N. Okay, so they are P extension. So fine. So now we are searching for very special property of absolute Galois group. And one of the very special properties, one of the first special property like that is famous Artin-Schreier theorem, which tells that the only finite non-trivial subgroup of GFs are group of order 2. So there is nothing more. This is it is not difficult to prove this theorem, but it is still fundamental and very important theorem. So if this means in particular is that if there is no group of order 2, these groups are torsion free. Okay, so there is no torsion in general. Yeah, I mean except this group of order 2. So okay. So now, as a complement to this Artin-Schreier, is still Artin-Schreier theory, that if GF contain an involution sigma, so this is the generator of this finite group of order 2, then the character of F has to be 0. And in fact, something more can be said. So if you define P to be all those elements in the F such that the sigma fixes square root of F, then this is an ordering of F. What does this mean, ordering? Most of you know it, but let me still call it. So this means that F is union of P union minus P, P intersection minus P0. There's multiplicatively closed and additively closed. And why this? So what is it? What is the meaning of this? It is called ordering because it defines linear order. So x is larger than y if x minus y belong to P. So this is the positive cone of your ordering. So in fine. So you know number of ordering in the real number, rational numbers, but for example, complex number have no orderings. Okay, so one can tell that, in other words, that P is a multiplicative subgroup of index 2 stable under addition, and it is important that -1 is not there. So okay, so now assume I would like to now do what I would call Artin-Schreier, small Artin-Schreier theory. So the Artin-Schreier theory was done in the large field, in the separable closure. So it would be nice to detect ordering on much smaller fields, and this can be done. And I would like to explain how. So now, so the notation again. So let F2 be the compositum of all quadratic extension of F. So you simply take every quadratic extension of your given field F, and you take the smallest field which contain them. It could be infinite extension. It could be also finite. And now, if they denotes again compositum of all quadratic extension F2 square root of gamma, where gamma belong to F2, and this F2 square root of gamma over F is Galois. So you put extra condition. It is not a repetition of the same condition as before because you put extra conditions that F2 square root of gamma over F is Galois. And so now I put the notation as a bracket notation for Galois group themselves. So the Galois group, so they're all Galois group. F2, F3 are Galois, that's easy to see. And therefore you can take Galois groups, and the notation for this Galois group is this bracket notation. So GF2 is this one, and GF3 is this one. Observe that this F2 is such a simple extension that this GF2 bracket, this is just so-called two-elementary abelian group. This means that every element of this group has order at most 2. So it is either 2 or 1. so 1, of course, if it is only identity, and otherwise 2. So in GF3 is also relatively small Galois groups, and I want to put it inside of exact some diagram here like that below, exact sequence, show the exact sequence. And in order to make it, I define GF2 will be Galois separable closure over F2, and GF3 the round bracket this time over F3. So, and then you see that this GF2 bracket is a quotient of GF3, and the kernel is GF2 over GF3. What is important is that both kernel and quotient are two elementary abelian. So we, in more or less, this GF2 over GF3 is center subgroup of GF3. Okay, so it lies in the center of this GF3. So it is, in a way, this extremely simple extension, and nevertheless, what is quite amazing, it captures quite a bit above this field. And we call it in Michel's pair of work, we call it sometimes this GF3 W group of field. This play a very important roles. So now let's go below. So now I want to show with one instance how you can recover ordering from this very simple small extension rather than the large extension. So I will consider involution from GF3 outside of Fertini. I will recall the Fertini in a moment. So it determines an ordering P sub sigma, and as before. So it is all those f such that sigma square root of f is for same as square root of f. And there is actually one correspondence. So you can capture all ordering in this way, and you can see how many of them in the group theory. So it's very nice because you can read your all ordering from the data from group theory, and the group theory is actually very simple. And so it is so the coset of sigma modulo Fertini give one correspondence of this ordering. Of course, you assume that the sigma is involution and sigma is not in Fertini. So what does it mean, Fertini of GF3? Again, most of you are familiar with Fertini, but let me still recall for this. So Fertini in general for group simply means it could be either topological group or finite group, and so. But in general, it means the intersection of all maximal subgroups. So proper maximal subgroup. Okay. So that is in particular for other thing. It is important that the Fertini of GF3 it fixes every square roots of f. Okay. So this is so now I would like to sketch the proof, and I will only concentrate what the most important part. So most of the things are actually quite easy in this proof, but there is one interesting part, I think, and namely that the ordering are additively close, and I want to concentrate on that. So here is what I told, that the main point is to prove that P sigma plus P sigma is under P sigma, and you can check easily that there is no problem, that it is enough to show that 1 plus P is inside of P for every P from P, okay, just by scaling if necessary. And so, and now, consider, so since sigma is not in Fertini, and I remember Fertini is exactly those elements which fix every square root, so, and sigma is not there, so therefore there exists some element B from multiplicative group of field, such that sigma acts non-trivially on the square root. And I put, I have to, I don't know why I put some, okay. Okay, so for some reason I did something. There was my hand over me, but now I get rid of it. Okay, so now we have so consider A and B from F star, there's a abuse of notation. I am using this B. This B is now in more general, right? It can be anything in F cross, right? I mean, the previously, and I will use it throughout the proof, the fixed B for a moment, but also for a moment, I will now allow any B, right? So you have two elements in F cross, and then the quaternion algebra A over B over F is a four-dimensional algebra over F. And the basis, so it is, you are familiar with it, even those who are not familiar with this notation, Hamiltonians are very familiar, right? So this is quaternion algebra over real numbers of this, and this would play a role of minus 1 over a real number. So this is generalization of quaternion algebra, of the familiar quaternion algebra, Hamiltonian. So now the basis of this thing is 1ijk, where J is the product of Ij and Ij anti-commute with Ji. So its relations are I square equal A, J square equal B, Ij equal minus Ig. It is very easy to show that this is actually indeed four-dimensional algebra, and it is central algebra. This means that the center is F, and also it is simple algebra. So it is central simple algebra. So, and now we say that it splits if it happens to be isomorphic as an algebra to 2x2 matrices over F. There is a very simple criterion, and this is exercise, one can do it without problem, that this happens even only if this A equal x squared minus by squared has a solution in F, okay, for x and y. Okay, so we build you can prove it, and but it's very useful criterion. So it tells that the binary form value of binary form will determine whether it splits or not. So okay, now I am not able to go down for some reason. Okay, yeah, I don't know. Yeah, I would like to go slides down, but I'm not able for a moment. Okay.
Jan, maybe if you exit the full screen and then go back to full screen again. So if you just press escape, the escape button.
Okay. It is frozen. Yeah, it is. Yeah, okay. So I'm back. So okay. So now, so we have this. So we know that it splits even only the solution. And now, I want to tell the following important claim. So if A over B splits, then sigma applying for square root of A fixes square root of A. Okay, so we know that sigma apply of square root of B does not fix square root of B, and so if you believe this claim, then BB over F cannot split, right? Because it cannot both fix it and not fix it, right? And so therefore I should perhaps prove first that BB does not split, and I will prove it. And the proof is very easy, but it relies on a little bit of Galois theory, on a very small Galois theory. So if BB splits, then B is, one can check, this is easy, that B is sum of two squares, and therefore you will have a Galois extension of degree 4, which is cyclic, so the Galois will be cyclic of order 4, which contains F squared of B. So in other words, you embed your field extension, quadratic extension F squared of B to cyclic extension of order 4. Okay, and abstraction for this is precisely that BB, the quaternion algebra BB. So if it splits, abstraction disappear, and this is solvable. So we can do it. And so we know that we have this extension. But if you have this extension, think about the sigma. So the sigma restricts to L, and sigma square is 1. So therefore, by Galois theory, it has to fix square root of B. But that is contradiction, because this again, it cannot both fix and not fix, so we get contradiction. Okay, so therefore we prove the special case that BB does not split. Fine. So now we want to do the general case. So the general case is when you take A from a multiplicative Galois field, but take away squares and take away B times squares. Okay, so then this thing F cross divided squares of F is called square class group, and the square class group is vector space over F2. So in this vector space over F2, because of our condition, this A and B are linearly in the classes of this are linearly independent. Okay, because I put this condition A is not in this and not in this. Okay, so and if furthermore A, B, and splits, then this is exactly the conditions similar like before, but not for dihedral extension, that there exists an extension L over F, Galois extension, such that F is under, by quadratic extension, F squared over F squared over B. Galois group of L over F is dihedral group over A. And the Galois group of L over F squared over B is a cyclic group over F4. Okay, so this is precisely the condition of embedding condition. Let me put diagram so that you can see it clearly. So this, I like this extension very much. So this is my smiling face because I'm happy that I got this extension. And so now in this extension, so by Galois theory, when you think about dihedral group of lattice of dihedral group and you turn this lattice around, then you get the lattice of subfield. And so in particularly you have 5 subfield of dimension 2. This means that L over K1 has dimension 2, etc. Okay, so and now I will put it. This diagram will not disappear. It is still on the other slide. So here we have it. And consider again a restriction of sigma to L, because sigma square equal 1. So it has to fix one of those. Okay. But we know that it does not fix the square root of B. So it cannot, so K3, K4, K5 are out. So it has to fix either K1 or K2. But it fixes any of those, then it fixes square root of A. But that is exactly what I wanted, okay? So it does not fix square, this is a repetition of what I told, but here is what I want. So then it fixes square root of A, so we get sigma square root of A over square root of A is 1, okay? So this end of this proof, because all this other part of these one-one correspondence and multiplicative subgroup, this is all easy. So the most important thing was to recover additivity property of ordering of this, which is here. Except let me still, there is still for this claim, but let me still complete its additive property because I didn't quite complete it. So let me complete it. So here is, so the first thing I want to show that -1 square root of -1 is not fixed, and how I will do it. So I will apply it again. So I know that B minus B over F is again split quaternion algebra. That's easy to see from this criterion. And now, again, applying this for substituting for A minus B, I get that sigma applying for square root of minus B is fixes square root of minus B. So, and therefore, from this, you get immediately, by just easy manipulations, that sigma square root of -1 is minus square root of -1. So square root of, so -1 is not in ordering, okay, not in the P sigma. So that's good. And now, if you consider P, any P from P sigma, so this is a little joke, it is not a prime number, so no confusion there. So sigma applying for square root of minus P is then, because of square root of -1 is not fixed and square root of P is fixed. So therefore it is minus square root of minus P, so that's clear. And now, however, you have another clear split algebra, namely 1 plus P and with one slot of this algebra and minus P is another slot. And so this is split because of this little equation here, but now this means when you think about this minus P, you now think about it as a B and 1 plus P as a A, then you get what you wanted. You will get that sigma fixes a square root of 1 plus p, and so in other words, 1 plus p belong to p sigma. Okay, so now the proof of the additively closedness is completed, and I told that all these other things are easy. So that's kind of thing. What is nice about this thing is that you could recover all of this ordering for this summary, this repetition, what I told that, or from this very small quotient of absolute Galois group. And this is kind of one of the theme which we found in the number of years, that the small Galois groups can tell quite a bit about the fields. It is very surprising in a way. And so, and now another instance is Viding. This is I will not go to definition because that would be too much time, but Viding of quadratic form is a natural ring made up from one element is 0 and isometry classes of anisotropic quadratic forms over F. So what does it mean, anisotropic? So quadratic form, you can view it as a function from your underlying vector space to your field. And if the only element in the vector space is 0, such that this quadratic form vanishes on these vectors, then it is called anisotropic. So, for example, sum of square over real numbers will be anisotropic because there is only zero vector will work. Okay, and now the quadratic form, Wittig quadratic form is very interesting invariant of fields, and very important, of course, for quadratic forms. And now the natural question is, we already recover ordering. Can we recover more? Can we recover Wittig of quadratic forms? Because ordering is known that they can be recovered from Wittig of quadratic forms. So okay. So and here is the answer is that not quite. There is some little small thing, but which is necessary. But it is nearly so. The answer is nearly yes. But if you ask precisely, the answer is no. Yeah. So let me tell you the precise theorem. So yes, suppose you have two fields. Then if the Wittig of quadratic forms are isomorphic as rings, then these Galois groups, which I call these W groups of these fields, are also isomorphic as the perfinite groups. And the converse is also true, but you have to assume just in one case, kind of, in when the form x squared plus y squared represent all elements in F cross, then square root of -1 has to be in F, even only if square root of -1 has to be in L. In other words, what happens is that if you assume that x squared plus y squared represent all elements in F cross, it turns out that the Galois group is blind to the existence of square root of -1 in F or not. Okay, if square root of -1 is in the field, x squared plus y squared always represent all elements in F, but it represents also in some other circumstances, and we cannot detect it just by Galois groups. So this can be seen that is necessary from a very easy example. So let's consider a field F equal FQ. Q is congruent 1 mod 4, a finite field, and another field with Q prime is congruent 3 mod 4, and then these both Wittig has the same number of elements, but algebraic structure are different. One is a group being over Z to Z, and the other is cyclic group over therefore. So they're different. So they are not isomorphic. But nevertheless, the Galois group GF, the W groups are isomorphic to C4. So it tells it this is a necessary condition. You have to have this condition. And okay. So now I want to go little bit further. There were some indices which I was using for tree, but you can generalize this filtration. So they are part of the more general filtration. It's very important filtration, Sassenhaft filtration. There's some other filtration on the perfinite group, on the absolute Galois group, but perhaps that it may be that the Sassenhaft filtration at this moment is winning. It is one of the most important, perhaps the most important filtration. But there are some other still important filtration. I mean, one cannot concentrate only on one. So and this filtration is like that. So suppose that G is perfinite group, P is a prime number, and so the first thing is G sub 1 will be just G. In this G sub n, you define recursively, you assume that you have all filtration below n, smaller than, slightly smaller than n. So then you take this group generated by all p's power from n over p, and here is the floor function, upper floor function of n over p. This means the largest, this means the smallest integer larger than n over p, okay? And so when this gi, gj, they are commutator, and so this group is mean, like usual in perfinite group, you take the group which is generated, it is a topological closure of all of this group you see. So we take all commutators in this group, all p's power, and then you take a closure of this. Okay, so it is we know this topological group, so we can take closure. And okay, so you have this, and now it is not difficult to check that the GNI normal closed subgroup, and this Gn over Gn plus 1 are p elementary abelian. So therefore, in particular, the FP vector space which make it very nice. And so with n equal 2, then this G2, this is actually 13 group. So it is subgroup. So for they might be yeah. I should make this is for Imnans for p equal 2. So they, I think there is misspelling in general. So it is G2p and GG. Okay. So it is p's power and commutator. So this is a 13 group. So there's misprint here. It should be GP. And so for N3 is G sub 3 is this group GP G2. So they're just some special cases of the previous definition. And for p equal 2 is slightly different. G3 has slightly different forms. So, but this makes this is important difference because the force powers this is generated by force power and only p's power. So here the index, when you divide by G over G3, index is P, and here index is 4 for P equal 2. So this is important. So, and now, if you assume that P equal 2 and G is this absolute Galois group, then this GF3, which I mentioned below, above, this is precisely this quotient GF over GF3. Okay, so am I covering kind of for more general Sasana filtration, the same quotient I was speaking about. Okay, and this quotient play an important role, this other quotient as well, but perhaps this GF3 is have a very special image about this other quotient. So now I define the Galois cohomology. So assume that ZP is this is a standing hypothesis, but I'm still calling here and there. Okay, so assume that this P's root of unity is inside of this field F. Then GF, this absolute Galois group, acts trivially of roots of unity. So therefore ZPZ is trivial module. And then one of the definition of Galois cohomology in this particular case, it is simply cohomology ring with ZPZ coefficient, and one can view it as a inductive limit of finite cohomology ring when this G is finite quotient of GF. Galois cohomology play extremely important role in all this investigation, and in the Rost-Voyevodsky theorem is related precisely to Galois cohomology. So this was formerly known as a Bloch-Kato conjecture. And I will not go to whole Bloch-Kato conjecture because of time restrictions. It's a beautiful conjecture. It's extremely interesting. But it was the first work on this was done by Milnoy in Invenciones 1970, then Bloch-Kato a little later. Milnoy was mostly concentrated for B equal to Bloch-Kato for all primes. And one of the amazing consequence of this conjecture is that the Galois cohomology is generated by, it is a graded ring, but it is generated by degree 1 elements. And this is a spectacular statement. It is, at the beginning, it was hard to believe it, that it is true. It is definitely far from true for finite groups, and I will soon make an example about that. And another consequence of Bloch-Kato conjecture is that actually this Galois cohomology is quadratic algebra. This means that it is generators are in degree 1, annihilations are degree 2. And we know even much more about generators. It is extremely interesting object. It's rather a simple object, but still it contains a lot of information about absolute Galois group, and it's a very, very interesting object. Okay, so now I am coming to alternative definition. So if you take this is a well-known definition. Let me go relatively faster. So if A is a discrete GF module, we set the continuous cochain of this GF, and then people are mostly familiar with this to A, and you define differential operator like that. So this is a well-known differential operator of this cochain. Then you check the dn plus 1 dn compositum is 0. So therefore you can take the cohomology of this complex, and you cover the Galois cohomology after with coefficient with A. Now it is more general. Okay, so we now in the Galois cohomology you have also the important thing is not just group, but it is not just graded group, but it's also graded ring. You have K product, so it is here, and if you have trivial coefficient, this K product is especially simpler. So it is if A, if B K product. So I like it to write it to think about coffee and think. So it is if A applying for the first A elements, or if B applying for the B elements, and you multiplying this easy. Okay, so that's it. And now I want to illustrate with one simple statement, but it answers also question of some work with Quadrelli and some other people, and it is kind of important thing. It turned out not to be difficult to prove, but we got the help. So with this work of Chebolu, me, okay, and but Benson gave us the key affines of small affines for this. So let me read it. So suppose that you have a finite group. P is a prime number, and P divides the order of G. Otherwise, it's not trivial. If it does not divide, then the cohomology disappears. So there's nothing to think about. So then cohomology. So now the statement: cohomology of this group, of the finite group, of this trivial coefficient is generated in degree 1, even only if so P has to be P, has to be 2. Sorry. And each silo 2 subgroup of G is non-trivial elementary 2 abelian group that admits normal complements. In other words, the G is semi-direct product of some normal group N on which silo 2 subgroup acts. Okay, so that is very nice statement. The special consequence of this, which we become first with it, is that if G is a finite P group and P is a prime number, then it's kind of easy to formulate. Then the cohomology is generated by degree 1, even only if P is equal to and G is simply 2 elementary group. So it is in 2 elementary group, this happens actually. So it is known, and this easy calculations, that if G is 2 elementary group, then it is polynomial ring in degree 1. Okay, so. And now let me make quick sketch of the proof. It is not difficult. So I'm trying to watch the time. I already lost some time. So let's see how much I will cover. So okay. So if G is P elementary abelian group, so the cohomology of this is well known and easy to calculate. So as I mentioned before, for P equal 2, it is polynomial ring of degree 1. For P odd, it is exterior algebra, this Yj or in Yj of degree 1 again, but over polynomial algebra when xj are degree 2, and they are in particular indecomposable elements. So in particularly, if you take elementary P abelian P group, then it is not true that it is generated by degree 1. So, okay. And so when you take this account, it is enough to show the following little claim, that if the cohomology is generated by elements of degree 1, then G is P elementary abelian, because then P by the slides by the thing above, P has to be 2. Okay, because for P odd it doesn't work; it is not a degree 1 generated. Okay, so and now. How do you prove it? So let's do relatively quickly. So if G is a P group, then the Fertini, as I told before, they will make this correction. this fertility group is this is easy to check by definition. So this again exercises intersection of maximal subgroup, and when you think about this, it has to be generated by Pavers, Peace Paver, and commutators. Okay. So now there is no topology; it's just that. So it is, and it is the smallest subgroup of H, such that G over H is a P elementary abelian, and it is enough to prove that. If G over ZP is generated by degree 1, then the fraternity disappears. So it is just trivial group. So fine. So now, so suppose it is not the case. Then there exists something which is in fraternity, which is not 1. And then we can also assume that X has an element, no, I mean, it is clear then that X has an element of void IP. And then, however, by Swan COM, we get the extraction of this extraction map of cohomology group of G over ZP2 to this subgroup is non-trivial in infinitely many degrees. But this cannot happen if we assume so for the following reason. Consider H1, G, ZPZ. Because the coefficient are trivial, this is nothing but homomorphisms. So it is homomorphisms of G to ZPZ. And similarly, H1 exists homomorphisms of X to ZPZ. And now, each homomorphism of G to ZPZ vanishes on fraternity group. That's clear, right? It has vanished on Peace Paver. And so, since X is inside of fraternity, it vanishes also on X. However, I call that this cohomology ring was assumed to be generated by elements of degree 1. So the extraction must vanish in all positive degree. So on one hand, it vanishes on all positive degree. Also, on the other hand, it's not trivial on all positive degree. It's a contradiction. So this proves the statement. So it is, the proof is not complicated, but the Swan theorem is deep theorem actually. So this is, we are using some deep theorem. Okay. And so now consider the following: that let G be a profinite group acting trivially of ZPZ, and we denote as a subalgebra of this, is a decomposable subalgebra of this is the subalgebra over ZPZ generated by one-dimensional degree elements. Right? So that makes sense. And now here we have some nice theorem. So this is another instance when we can tell that the very small quotient of absolute Galois group determine, in fact, entire cohomology, Galois cohomology. It is surprising. It's very interesting. So it is. So we tell that if N is a closed normal subgroup of GF, then the inflation map, when you take GF quotient by N with ZPZ, decomposable part of it, then you get isomorphism. This is a misprint, but it's meant to be isomorphism, even only if N is inside of GF3. So in other words, it works for GF3. And so this means that GW group determine entire Galois cohomology. This is very interesting result. I am very fond of this result, and it's used many times. Okay, so now there is another structural result which we get also with Ido effort. So assume that P is an odd prime and F is a field containing this, then this GF3 is intersection of all normal open subgroup N of GF, such that GFN is isomorphic, just a cyclic group of void P or Heisenberg group of void P cube. So let me recall, Heisenberg group of void P cube is a non-abelian, it is determined by this property. This non-abelian group of void P cube in exponent P. Right? So this is well known that there are not many group of void P cube, right? And so in non-abelian, you can classify them by two types, and one of them is Heisenberg group. And the interesting thing also for later on for massive product, that this HPQ is actually isomorphic. This is easy to show. Is a unipotent group of void 3 times T over FP coefficients. Okay, so it is clear that there's P cube element because these stars can be filled by any element in FP. Okay, and so why it is so important? It tells you that if you take this W group of this, that it is actually or let's say F3, the fixed field of this, this is generated by Galois extension of extremely simple type, surprisingly simple type. It is only cyclic elements or cyclic Galois extension, which is Galois group of ZPZ or a Heisenberg group of HP cube. And this is very, very useful because if you want to check certain annihilation, you have to check only this annihilation on this particular Galois extension. This is an extremely useful statement. And you wonder what happened for P equal 2. That was done much sooner. So with Michel Speer and also Villegas, so it assumes that P is equal to and character is equal to, and the result is analogous. So it is the same kind of result, except you replace, so you have Z to Z, and there is also another instance, because remember that the Sassana filtration, you can have also exponent 4, so it is also cyclic group of order 4, and dihedral group of order 8. So dihedral group of order 8, therefore, should be viewed as an analog of Heisenberg group. So you should, so you have two group, non-abelian group of order 8, quaternion and dihedral, but dihedral is the right object to consider. And indeed, it is also dihedral group is also isomorphic to U3 over F2. So now we are coming quickly to massive product. Okay, so let me quickly. I want to at least formulate this massive product and tell a little bit about this thing. I'm very excited about this thing. It is a fascinating thing, and it is a void in the progress. Yeah, there's a lot of things prove, lot of things are known. So let me begin. So you have G is per-finite group, P is prime, A is the cochain algebra, you have product. So I'm defining actually on this cochain, I am defining differential graded algebra. So on the cochain you can define product itself. We defined it already product on the cohomological classes, but you can define it on the cochain themselves. And then these cochains satisfy the usual properties, associative, and the differential, the same differential as before, satisfy the famous Leibniz product formula. So it is like that. So now here are the key heroes of the story. So assume n is larger or equal to. So then you consider the unipotent groups, and for technical reason I consider un plus 1 rather than un. Okay, so that is not that important. I could begin with n equal 3 and then and so on. So okay, so and this is simply, they are upper triangular matrices with FP coefficients. So this generalization of Heisenberg and the dihedral group of order 8. And it is also easy to see by just counting that it is a P-Silov subgroup of GLN plus 1 FP. Okay, and now we can define the usual coordinates map Uij to ZPZ. So these are mapped from UN plus 1 to ZPZ, and observe, this is not difficult to prove either, that of UN plus 1 under this condition is this is the Z. This you can actually know what is it. They are all matrices that all entries are 0 except the upper corner. So of course diagonal has to be 1 because they're upper triangular, but the upper corner can be anything. Okay, so this is the center. And then you take the quotient UN plus 1 bar. This is UN plus 1 divided by Z. So this is the quotient like that. And you can actually manipulate these matrices like this. Interesting. This is just before, because these elements here are 0, 0, 0, and so on. So there's some fun thing. You can check it quickly. That if you consider the upper corner removed, then you can manipulate these matrices. No matter what you would fill in the upper corner, it doesn't matter because it doesn't affect the other coefficient. Okay, so you can work with this UN bar, but it is this quotient if you would remove this upper corner. Okay, so fine. So you have this. So we have the sequence as I mentioned, and consider also, and this is very, very important. Now I will use a little bit of Merkouriev's caviar notation. So they make some wonderful lectures about this massive product, which I love very much, and they make also very nice notation. They're very good also, not only researcher but the expositor, and so I love this notation. So this, you have this homomorphism which I mentioned before, and then you have also homomorphism on the near diagonal. So this is just one line parallel to diagonal, above diagonal. And this has ZPZ to N, because that's clear. And so, and now consider N character. so this will be on this kind of which play a role in the diagonal. So there will be n character of the of your perfinite group to ZPZ. So they are just homomorphisms because we assume that it's trivial action. And now you have this G, this chi will be this upper triangle. And there are two questions. Can we lift it? This homomorphism chi, you assume you have this already, this homomorphism chi. Can you lift it to rho bar, to U n bar? That's the first question. Second question, suppose you can lift it. Can you then lift it to rho, to un plus 1? And this is extremely important from Galois point of view, because you would like to realize a subgroup of un plus 1 bar or un as a Galois group. So it is something extraordinarily interesting. And so let me now come to this and let's make this picture again. So here is this rho bar, this you can picture this matrix like that. Okay, so that would be, and the reason why I picked the first row and last row like that will be clear in a moment. So it is I'm coming to the so here is the things that if they exist, lift over rho bar, we can write, so we can fill this upper corner by eta, and when you and this will be some continuous cochain, okay? But now you think that this is to be homomorphisms. This rho is homomorphisms of G to these unipotent matrices. And if you just calculate what does it mean, and then now you see why I put this first row and last column, because it plays important role. So then you get the wonderful formula which is written here. When you think there's eta xy minus eta x minus ay, this is actually minus of delta operator of eta. So it is co-boundary of eta. Okay. So this will be clear from next slides. So it tells that, in other words, if I make this notation, which I borrow from Merkoyev's caviar lectures, so this delta rho by xy, so this is this product, this essentially scalar product. You can think about this of the first row and the first column, except the thing which is deleted on the upper corner, and this is always cocycle under this constitution that you assume that the rho by is homomorphisms. This exercise one can show it. And now, then, rho exists even only if the cohomology class delta rho vanishes. And this is clear from the previous slides. So let me perhaps write here, because this is this delta rho bar here, and this would be it is shown that it's co-boundary. You see, from this. So okay. So you will get this one. So that's wonderful. And now here is, so at least I go to the definition. That's great. So okay. So let's G be a perfinite group, P is be a prime number. Suppose the G acts. Do I have enough time still, Paiman? Can I still continue?
Maybe 3-4 minutes.
Okay. Let me be fast. So okay. So the mod P massive product of X1 is the set when you take all these cohomology classes from this, when you say assumes that it's defined, and if it vanishes with content 0. So this means that if it is defined if rho bar is realizable and it is vanishes if rho is realizable. So it is incredibly nice if it vanishes, because this means that something automatically, some Galois group miraculously appear. It is incredibly thing. And now in the case when inequality, I will now skip it of this, but one can specialize. It is already very interesting on inequality. So I will skip it because of time, but it is interesting. And so we prove that in particular we stand that if f is a characteristic distinct from 2 and you have alpha beta gamma such that alpha times beta equal beta gamma equals 0, then alpha beta gamma always vanishes over any field. And this already tells that number of Galois groups are automatically realizable. It is wonderful thing. And motivated by this, we made the following conjecture. This is sometimes called massive vanishing conjecture, and also they attribute it to us. This conjecture that it's n equal t, be an integer, and p is a prime number, and you have this n character. If it is defined, then it vanishes. And so far there was not find any context, but actually there was some wonderful result concerning this, and this is my last slide's promise. Okay, so here is this. So the following result were established. So if f is number field, so Hopkins and Wickelbank shows that it is true for n equal to p equal to, even before our conjecture. And if n, before we formulated this conjecture, if n is any field n equal to p equal to, we prove it. And if any field n equal to n prime, Efrad and Massa prove it, and also me and Tana prove it. And if f is number field, we prove it for n equal 4, p equal 2 with Galois, me and Topaz and Wittenberg help us in a very important way. And then the great result quite recently is that for all fields, if n equal 4 and p equal 2, Mekoyev and Skavia prove it. This is a wonderful result. They used the previous result what we was working with Galois and Topaz. And so, and they were able to show the certain equation that solvable. Is a fantastic. And then the spectacular result is, and this gives me some kind of comfort, is that additional to previous results, that if f is number field and n is larger or equal to 3 for all primes, it is proved. So the full conjecture is proved by Hypers and Wittenberg. This wonderful result. Some results are easy. There are a number of easy results. So one of the, but they are important one, for example, for using local global principles. So if is local fields n larger or equal to any prime, we prove with Turner that it is true. So. And now there are a number of other results. There are a lot of people working on this. I'm very happy. I'm very grateful to all of these people who are working on this. It's a very, very exciting time, right? And so there are Bleher, Chimber, Gilbert, Efrat, Gio, Lam, Leo, Matzai, Mekoyev, me, Park, Quick, Quadail, Shai, Fitan, Weg, Wang, and a number of others. There's a lot of people are working on this. It's a really exciting time, and you are most welcome to join us. I would be very happy if you join us. Okay, so now here it is the Sherlock Holmes just found together that the massive vanishes. So there is this thing, and here are a few references. So I will not go over this, but there's relevant references to this talk. And so you can see there is number of the Sasha Merkuyev and Federico Scavia. I wrote number of papers I know recently, which I'm very, very excited about them, and some other papers. And there are also this paper with Stan, which I mentioned, and with Michel Spear, and also Claudio Quadaili, and so far another. And so finally, thank you, merci beaucoup, and ďakujem veľakrát, this is in Slovak class. So thank you very much. So if you have any question, I am very